Welcome back. Let's just do a few more examples of implicit differentiation. For this one, we're looking to find a normal line. A normal line is just the line that's perpendicular to a tangent line. And of course, you know the relationship between slopes for perpendicular lines. You know that the perpendicular slope would be the negative reciprocal of whatever slope you start with. So since dy dx, since our derivative gives us the tangent line slopes, then -1 over the derivative gives us the slope of our normal line. So here we've got this equation, root of x plus root of y equals 7, and we want to find the equation of the normal line to that curve at that point 916. So the first thing I want to do is find the slope of the tangent line at 916. Then I'll find the perpendicular slope, and that'll be the slope of my normal line. And then once I've got that, I've got my slope, I've got my point, I can go ahead and find my equation. So I'll begin by taking my equation and I'm going to differentiate both sides with respect to x. And of course, as always, square root of x, I'm thinking that as x to the 1/2. So when I take the derivative, it's 1/2 x to the -1/2, which is the same thing as 1 over 2 root of x. And same thing with root of y, it's 1 over 2 root y. But of course, I need to remember that y is a function of x, so the derivative of y itself is dy dx. Right here is going to be a common place where people will make a mistake. A lot of times people will, for this equation in particular, just put a 7 down on the right side of the equation and forget that we're supposed to be differentiating both sides. And the derivative of 7, the derivative of a constant, is 0. So there we go. We just need to be a little bit cautious with this. That's a very common and very casual error to mistake to make, and we don't want to make those sort of errors. Okay, so now let's find our derivative at 916. So same thing as previously when I was finding a numerical value for my derivative. I'm not going to bother doing any simplification just yet. I'm just going to put in the 9 for x and the 16 for y, and that'll make it faster for me to solve for my dy dx. Root of 9 is 3, so for that first fraction I have 1 over 2 times 3, which is 6. And root of 16 is 4, so for the second fraction I have 1 over 2 times 4, which is 8. And there we go. I can go right ahead and solve for dy dx. There we go. And bring the 8 up. That'll give me -8/6, which is the same thing as -4/3. So -4/3, that's the slope of my tangent line. Slope of the normal line then should be the negative and reciprocal of that. So since my tangent line is slope of -4/3, my normal line should have a slope of +3/4. And so now let's go ahead and create our equation of our normal line using y minus the y coordinate equals slope times x minus the x coordinate. And for my point, reminder that our point that we were looking at was 916, so putting in 16 for y, 3/4 for the slope, and 9 for x. And then just a little bit of cleaning things up, and I'll have the equation of my normal line. So I've got 3/4 x minus 27/4 plus 16, and -27/4 plus 16 is 37/4. And there we go. We have the equation of our normal line. Okay, here we're looking to find the second derivative, d squared y over dx squared. So nothing really shocking or new here. As always, if you're looking to find the second derivative, you do it in two steps. Find the first derivative, then find the derivative of the first derivative. Where this is going to get a little bit more complicated is that since this is an implicitly defined function, then I'm going to wind up more than likely with a first derivative that's also implicitly defined that will have y's and x's, which means that my second derivative more than likely will have y's and x's and also dy dx's built into it. So it's going to take a little bit of extra work to simplify our second derivative and make it a little bit more reasonable and useful. And we'll talk about that as we go a little bit further on. But let's start off with finding our first derivative. So if I differentiate both sides with respect to x, so I have 9x squared, the derivative of that. Power rule says the 2 comes down, so 9 times 2, 8. So that's 18, x to the 2 minus 1, which is 1. For the derivative of 4y squared, same sort of thing, we're using power rule, and of course, derivative of y is dy dx. And then on the right side, 36, the derivative of that constant is 0. So I'm just going to clean up and solve for dy dx. And I've got negative 18x over 8y, or simplifies to give me negative 9x over 4y. And there we go, that's my first derivative. And of course I said I wanted the second derivative, so I'm going to take my derivative of that, differentiate both sides, again with respect to x. So on the left side, I have the first derivative, and the derivative of the first derivative is the second derivative, so the left side is not terrible. But on the right side of my equation, you'll notice I've got a quotient, which means now I'm going to need to use quotient rule. So let's do that. The bottom gets squared. 4y, when I square it, it's 16y squared. Then the bottom comes up, 4y, times the derivative of the top. Derivative of negative 9x is negative 9, minus the top as it is, so minus negative 9x, times the derivative of the bottom. And the derivative of 4y is 4, and the derivative of y is dy dx. And so this is what I mean about the issue that I've got here now with my second derivative. If you wanted to find a value for the second derivative, if I said, please find the second derivative at such and such point, you'd need to know the x value and the y value for that point, but you'd also need to know the value of the first derivative too. So as it currently is written, this is not a terribly nice second derivative. I'm going to do a little bit of cleaning things up. So first thing that I'm going to do is, of course, multiply the 4's and the 9's together. So when I do that, I'll have minus 36y, and I've got a plus 36x dy dx. And that's all over 16y squared. So what I'm going to do now, now that I've done a little bit of cleaning things up, is I'm going to get rid of that first derivative. And by getting rid of it, I mean I'm going to substitute in, instead of having dy dx, I'm going to replace that with minus 9x over 4y. And of course I can do a little bit of cleaning up here. As far as things go, I'll have that the 36 and the 4, I can cancel those together, leaving just 9 behind. So I'll wind up having a nicer looking negative 36y minus 81 x squared over y, and the whole thing over 16y squared. Now you might say to yourself, that does not look terribly wonderful, and I would agree with you, but there's a little bit more that we can do. First thing being, I have fractions inside of fractions, and I'll fix that right away by taking the second derivative and multiplying everybody on the top by y and everybody on the bottom by y. So that I'll have a minus 36y squared. For the second term, the y's cancel, so I have minus 81x squared. And then on the bottom, I'll have 16y cubed. So one thing you might notice is that at the top, at least, the 36, the 81, those are numbers that 9 both go into. And if you factored 9 out, or more particularly, if you factored negative 9 out, then something kind of nice emerges here. It doesn't always happen this way, but it kind of nicely happens for this equation. That you'll see that on the top, after I factor negative 9 out, I have negative 9 times 4y squared plus 9x squared. And you might say to yourself, well, how is that nice? And I'd say, if you remember the original equation that we had, it's flashing back to it, 9x squared plus 4y squared is the left side of my equation. And for this equation, 9x squared plus 4y squared is always equal to 36. So in other words, that 9x squared plus 4y squared that I have, I can replace that with 36. I can say that actually my second derivative is negative 9 times 36 over 16y cubed. And then I could just do one last little bit of cleaning things up there. I can divide top and bottom by 4 to give me negative 81 over 4y cubed. So as a sort of fun little twist here, after we found our second derivative, it turned out our original function fit into that second derivative, and we were able to use that to help us simplify. And that is something you will sometimes see pop up when you're looking at higher derivatives of implicitly written functions. Okay, the last little topic for us to look at is orthogonal graphs. Graphs that are orthogonal are ones that when they cross, they meet at a 90-degree angle. Or in other words, that the tangent line for the one function is perpendicular to the tangent line of the other function when the two things cross. So what we're looking at here is x squared plus y squared equals 40, and showing that it's orthogonal to y equals 3x. So first off, just as far as does this seem to make sense, as far as should we expect that they're orthogonal, if you know what the graphs of these functions look like, then the answer is pretty clear as a yes. We have x squared plus y squared equals 40. That's a circle whose center is at 0, 0, and radius is square root of 40. And y equals 3x. That's a straight line going through the origin. Of course, if you're looking at this, the tangent line to the circle does appear to be crossing that straight line at a 90-degree angle. So I have a feeling that we're probably going to come up with a big yes to this question, that yes, the line y equals 3x is orthogonal to that equation x squared plus y squared equals 40. Okay, so let's actually show this, though. If we want to show this, we need to show that at the points of intersection, that the tangent lines are perpendicular. So I guess our first thing is, where are the points of intersection? So here I've got one equation that's x squared plus y squared equals 40, and the second equation y equals 3x. So I'm going to substitute that second equation into the first one. So when I replace the y with 3x, then I'm going to get x squared plus 3x that's been squared equals 40. That's x squared plus 9x squared, or 10x squared. So I find that x is 4, which gives me two possible values for x at positive 2 and negative 2. And then I want to find my values for y, so I'll need to go backwards and say, well, I know that if x is 2 and y is 3x, then y is 3 times 2, which is 6. So one point of intersection is the point 2, 6. The other point of intersection happens when x is negative 2. And for that, the y value would be negative 6. So the other point of intersection is negative 2, negative 6. So we have 2 points of intersection, which is kind of what we saw when I did a quick little sketch of a circle crossed by a line. That was 2 places where that line crossed. So I feel confident that we found all of our points of intersection. And the next thing we need to show is that the tangent lines for these 2 points for the 2 curves are perpendicular. If we're looking to show that things are perpendicular, that involves knowing what their slopes are. And if we wanted to know slopes of tangent lines, we need to find derivatives. So let's start with the first one. I'll start with the easiest equation. So for y equals 3x, the derivative is just 3. So that means at both 2, 6 and at negative 2, 6, negative 2, negative 2, 6, the slope of the tangent line it's positive 3. Okay, so now we need to do the same thing for the circle, the x squared plus y squared equals 40. Find the slope of the tangent line at those 2 points to that curve. So for this one, it's implicitly written, so I'll need to differentiate both sides implicitly with respect to x. So derivative of x squared is 2x. For y squared, it's 2y dy dx. And derivative of 40 is 0. And then now just a little bit of cleaning things up, and we find that the derivative is negative 2x over 2y, or same thing as negative x over y. So at our very first point, which was 2, 6, the slope is negative 2 over 6, which is negative 1/3. And at the other point, negative 2, negative 6, the slope is also going to be negative 1/3. So we found that for the straight line, the slopes of the tangent lines were 3, and for the circle, the slopes of the tangent lines at those 2 points were negative 1/3, and for sure, a slope of 3 and a slope of negative 1/3, those are slopes of perpendicular lines. So we have found that when these 2 curves cross, that the tangent lines at those points of intersection are perpendicular, so therefore the 2 equations are orthogonal.